Hi, everyone.
Hello.
You should be able to see my slides now, right?
Yeah.
Thank you. So we'll start in about 9 minutes. So while we're waiting, anyone have any questions about the course, about logistics, about the course, project selection?
Could you give us some like example projects people have done before, just to give us some idea on the scope of what we're doing?
Yeah, definitely. So for example, one of students from my group who took this class 2 years ago work on the project called Habitat, where he tried to essentially predict the runtime of DNN training jobs running on one GPU onto a totally different GPU, so without ever training or running on that GPU. So that's interesting because that would allow to build a tool that could make educated guesses on how your model would run on a different hardware without purchasing that expensive hardware. So this is one example. Another example, I think another student of mine, Hanji, worked on the non-volatile memory project. So the goal was to see how we can efficiently deploy these new NVM memories in their, for existing applications in the cloud. So that one of the problems we look at, what would be the overhead of deploying NVM if it's used as the main memory rather than just the storage. So using this as the memory obviously adds up some latency, so you need to compensate for that, but it gives you way more memory. So it's very efficient cost-wise, it's a very efficient solution, but the goal was how to minimize the overhead. This is another example. There were several examples from the people from EC department that have worked on the, on something related to their research in EC department. For example, they work on the chip design that can, reduce the precision for inference, for machine learning inference. So you can reduce the number of bits you need to store, which reduces the footprint, which is critical if you try to run machine learning on really small devices. So this is a couple of examples. There are obviously people coming from the other areas like programming languages, and they did something related to their areas and architecture.
Okay, thank you.
Yeah. Will be the recording lectures posted? One question to get there. Yes, like every time we finish the lecture, the slides and the recordings will be posted online. So for the last week lecture, the recordings are already posted. So you're gonna get a link to both YouTube and their shared media from UofT. Just go to the schedule of this class on the course website. Okay, any other questions? Okay, I guess let's start. So last time I talked, and yes, as usual, thanks, Pavel. Guys, if you can turn on your video, that helps a lot. Last time we talked mostly about general terms about importance of architecture, about how you should do research properly, how you should look for your, research topic or the agenda you're interested in research. It was not particularly technical, right? So I didn't scare, I guess, a lot of people today, but last week, but I might scare some people today, I guess, when we go into more technical stuff. So some of the content I'm going to cover today is covered in undergrad computer architecture classes, are not that deep. So for some people who already took advanced computer architecture in the undergrad classes, there can be quite some repetition. But I need to make sure in the first few lectures, I would put everyone on the same board so the background kind of evens up for everyone, because some people here in this class don't have computer architecture background, right? So for people who took those classes before, sorry. But yeah, hopefully in a few lectures, we will see more interesting content. And one thing, again, I want to remind everyone, this is supposed to be more like a research active seminar. So you're not gonna, I don't anticipate myself talking for 2 hours, right? So I expect you will interrupt, question some of the stuff I do, question the relevance of some of these older results that we're gonna have on the graph. Some of the graphs I'll do, like maybe 3, 4 years old. And the question you can always ask is like whether these trends are true, whether things change, and things like that. So it's totally legitimate to interrupt. We had a relatively small class, so you essentially can just interrupt myself, mute yourself, and ask a question, right? So you don't have to be just using chat alone, right? Just make sure that just only one person talks at a time. Okay, sounds good. Okay, let's move on. So today we're going to talk about parallel processing and multicores. So what we're going to cover at the beginning is parallelism, multiprocessing fundamentals. I'm going to repeat Amdahl's law. That's the corner case law that you're supposed to know in computer architecture, which is good for any system level research. We're going to look at a lot of different multi-cores architectures, why they're needed, why they came up, and what are the alternatives right now, and why people ended up using them versus those alternatives. So we're going to discuss all different alternatives that people have. You're going to see a lot of examples of the real chips, not necessarily the brand new chips, but you're going to see a good summary of their different type of CPUs that exist at different times. Okay, so we first start with Flynn's taxonomy of computers that was introduced back in 1966 by Mike Flynn. So there are 4 major types of architectures. There's obviously single instruction that operates on single data elements. That's called SIST, right? There is CMD that I guess a lot of you've heard if you, do some low-level optimizations on modern CMD, modern CPUs. So this is single instructions operating on multiple data elements. CMD became very trendy probably around 2007, 2008. That's where it was first adopted in the modern hardware, like, Intel chips start to use it very widely. And then compiler starts to support that. So first it was used in a very narrow domain, like graphics. Then it gradually moved more aggressively to more general purpose domain. Right now, if you buy a modern CPU, right, like from Intel or AMD, if you actually want to get the peak performance out of it, whatever is claimed to be the performance, you're never going to get that without using CMD instructions, right? Just regular instructions. And memory bandwidth, everything is over provisioned for be using, single instruction, multiple data elements, right? It's like making 16 adds in parallel. If you're going to try to do individual instructions, you're barely going to use, like, 30% of your memory bandwidth. You cannot separate it. So this is essentially the key to get performance from modern CPUs. So there are 2 types. We're going to talk about array processors and vector processors. Then there is multiple instructions operating single data elements. So the closest form that we usually don't teach, but recently gets very popular is systolic array, right? So this is something that multiple instructions operate on a single data element and trying to efficiently utilize the existing hardware. And there's some of you that in the area might have heard about tensor processing unit from Google that use machine learning acceleration. And those tensor processing units are built on systolic architecture. And pretty much any other fancy, startup that claims to do machine learning hardware right now uses systolic array architecture. It's quite old. It was invented back in the 70s, 80s. It was never actually used so actively until the machine learning and matrix multiplication in particular become popular. Another example is streaming processor, right? Streaming processor just runs single instructions and a lot of different data elements. Sorry, a multiple instructions, just single data element. And there is multiple instructions operating multiple data elements. So it's multiple instruction streams happen at the same time. So this is multi-threaded processors. Any multiprocessor belongs to MIMD architecture. Okay, so all these architectures exist right now. I guess the first type is very rare, but that's the original classification that was introduced and still used to this day. So whenever we're going to talk about different machines or different techniques, you always try to think about where they fit into this taxonomy, because it kind of gives you a sense what they really do. That's usually the first piece of the taxonomy. Okay, So first questions we ask, because we're going to talk a lot about parallelism, about parallel architecture, about parallel programming. So why parallelism is important for computers? Well, parallelism allows us to do multiple things at a time. So those things can be different. It can be instructions you can execute in parallel, operations, tasks. I guess I'll pose the questions to you. So why would you ever want parallelism? Why would just not optimizing everything perfectly and doing everything, two instructions for one data element or something like that? Why we need some form of parallelism? Like why it was always an integral part of the architecture? So any ideas, guys? What do you think why parallelism was so early in the design of hardware, even before it was practical? Pavel, go ahead.
Well, maximize throughput, right? Well, even if we max out the single thread, you still won't be able to process as much as if you do like a massively parallel computation.
That's definitely true. Although back early in the day, they didn't really focus on throughput as much. They focus way more on latency, but it's true these days. Yeah, I think Alex here said that 2 things at once is better than 20 at once. That's fundamentally true. So essentially, one fundamental problem with hardware is you have to work for different applications, right? So it's almost impossible to figure out the exact ratio of everything needed for a general application, because one application needs 2 adds, 1 load at a single cycle to do the, say, hot loop. Another has a totally different shape, right? Which means no matter which hardware you're going to build, there are going to be some resources underutilized. It can be underutilized severely. This hardware underutilization is very undesirable, right? Obviously, you don't want to waste silicon. Back in the day, it was extremely expensive. So people start to think about, if something is not utilized, can I use multiple things in parallel, right? So that resource would be more saturated than otherwise would do. So hardware utilization is one of the driving forces of this thing. Okay. So let's move on. So the main goal is improve performance, execution time, or task throughput. And as I said, at the beginning, the more focus was on the latency, execution task. Most of if you read like papers from 70s and 80s, no one talk about throughput. Everyone talk about latency, right? And execution time. It was the primary metric. Throughput came later. But this is why we need parallel computers. So execution time of a program is governed by the Amdahl's law, and that we're going to talk about in the next 10-15 minutes. There are other goals that are especially important right now. They were less so important in 70s, 80s, 90s. Up until mid-2000s, it was not the major limiting factor, but now it is. It's at power consumptions. So one trick here is that the dependency is not very linear. So for example, I might have 4 compute units, right, that runs off a quarter of a frequency, and they would consume less power than, one unit, n units at frequency f. So it really creates you a trade-off where you can have fewer, less powerful units being more power efficient, right? But the question would be how to get with them similar performance, which can be tricky. So any ideas, anyone with an engineering background, let's put it this way, why does this happen? Why if we reduce the size of the compute units, the frequency goes, and we use the frequency proportionally higher compared to the size of the unit, why we consume less power?
May I answer?
Yes, go ahead.
I think it's because the chips end up being smaller, so the signals have just less distance to traverse.
That's correct, but why wouldn't it be linear? So it's like, why wouldn't be that as I reduce the size of the unit and I proportionally increase the frequency at which I operate, why would the power won't be constant? So essentially, normal equation, if essentially frequency and the size, right, are related, right? So, so if I make things shorter by increase this, like think about the linear wire, right? Right. By the way, just give me a second. Something went wrong. Just give me a second, guys. Something went wrong on my end. Okay, sorry, some technical issues. So you should be able to see. Okay, you can see my slides, right? So let's see who posted them. Yeah, so I think Behrus, sorry if I mispronounced your name, you're correct. So the problem is that if you look at the equations for the power, right, then you would see that the frequency there is not linear, it's actually quadratic at least, right? So it means that if I reduce the frequency by a quarter, right, I would actually reduce the power by 1/16, right? So this is why it's such a desirable thing to do. But if you go too small, you cannot run as efficiently. You don't get enough transistors to cut the latency. So there is a trade-off here. So you might reduce the power consumption, but you also might reduce the performance of your chip. So this is the trade-offs people have to deal with. But the main thing is non-linear. If it would be just a linear relationship, like that's what I guess Jimmy was pointing it, if it would be just a wire, that if I would just reduce the size of the linear of the wire, but increase the frequency, which would be the speed of going through that wire, that would be just make it equal, right? The problem is that the power is not just managed by that law. Any questions about that? This is just, I mean, not everyone has the engineering background, but just for you to understand, we're going to relate to this frequently. When you trade different parameters, right, depending on the physics of the device, it might not be a linear dependency. So you need to go and refresh your physics background and see what the relationship is. In the case of relationship between power and frequency, it's usually quadratic. Okay, any other questions? Okay. So another important goals in terms of improving performance, is improving cost efficiency and scalability by reducing complexity. So it's harder to design a single unit that performs as well as n simpler units. So smaller wimpy nodes are easier to design, and that plays a role. And obviously cost efficiency and scalability in designing chips. There's all these trade-offs. So like computer architecture, all full of trade-offs. You're always going to trade in one for another. It's rarely going to win in all possible dimensions. Okay, I think Mustafa raised hand. Go ahead and ask question.
Yes, I just have a question. You said that what do you say, the ratio between the power and the frequency is quadratic?
There are two different formulas depending on how high of a frequency you operate, but in general case, I think it's quadratic.
Because I was reading the paper yesterday and they seem to be trying to fit like a cubic for the Pareto frontier for it. So it would seem to me that there's a cubic relationship because they're trying to fit that really, like on the power and performance scale.
I think essentially it's not neither quadratic or cubic if you want to be accurate. It's just approximations, right? So, and depending on which range of powers you operate, it can be either quadratic or cubic or closer to it, but it's neither a precise opinion.
I see.
Yeah. So it's unfortunately more complicated than that. The key thing to know here for this question, it is never linear. Any other questions? Okay. So there are different types of parallelism and techniques on how to exploit that. First of all, there's instruction level parallelism that if you took a computer architecture class before, you would learn already. So different instructions within an execution stream can be executed in parallel. And that's exploited by a lot of different optimizations that I won't be able to cover in this class, but hopefully you cover at least somewhat in your prior courses. This is pipelining, it's an out-of-order execution, it's speculative executions, and something called very long instruction word architecture. That's where you execute multiple instructions all in parallel. There are also architectures called data flow. The most notable example of that was a TRIPS architecture from University of Texas at Austin. I think several leading people from that are now in industry right now doing real designs. Data parallelism is another type of parallelism that can be very efficient. So different pieces of data can be operated in parallel. So vector processing, CMD type of processing is a very useful example of it. Systolic arrays or streaming processes, that's another example. There is also something called task level parallelism. This is when the application is built of tasks or threads. Those units can be executed in parallel, and that's very well supported using modern programming technologies, such as using multi-threading or multiprocessing using multicores. So if you had that extra level of parallelism building your app, or you can somehow extract it from your applications automatically using compiler, that's good and can be exploited using multi-threading and multiprocessing. Okay, so those are the major types. So task level parallelism can partition a single problem into multiple related tasks or threads. It can be explicit when the programmer is asked to write the threading model, and that's easy for the programmer when the tasks are natural in the problem. And for example, if you by default have a simulation and you can run multiple different environment testing through simulation of some sort in parallel, that's a very natural, easy way to parallelize it. The problem with explicit parallel programming, it becomes difficult when the natural test boundaries are unclear. When you get a regular sequential code and the most programs and algorithms we wrote are actually typically sequential, then it becomes a problem. Like it's not easy to explicitly write what the task or thread should be, so that parallelism is not easy to exploit. Another strategy is transparently or implicitly. So that's a thread level speculation technique. So it can partition a single thread speculatively. So this technique trying to figure out, say, two branches or two different streams of instructions on your single application thread, right? And then try to run them in a separate independent threads with the minimal communication between the two. So this is usually done using compilers. Another thing is run many independent task processes together. The easiest example is like, you're trying to deploy some form of AI or machine learning model in the cloud, right? And you had a lot of customers. For example, I don't know, you had a web service for something like Siri, and you get all the speech recognitions that come in at you. They're all independent. There are a lot of them. So you get a lot of parallelism through just handling a lot of parallel tasks this way. So it's very easy when there are many processes. You can do different types of batch simulations from different using all forms of cloud computing services. It's a very good fit for that. So when it works, it's amazing. The problem is that it doesn't really improve the performance of a single task. So if you had a single threaded one application that you care about and you don't have neither batching or different users or this big cloud computing case, none of that is applicable to you. Okay. So those are the key things that exist. We just scratched the surface, and now we're going to talk more about multiprocessing fundamentals. So multiprocessors have different forms. So there are loosely coupled multiprocessors that have no shared global memory address space. There are multiple computer network that are network-based multiprocessors. Those loosely coupled multiprocessors usually program via message passing, something like MPI. The explicit send receives information. So it's like if you want to communicate between two entities, two processes, one send the message, said, please wait something for me, and then On the other end, you write a receiver code, and that, so all communication is essentially explicit, right? So for many, many years, so that's one, camp, and there was another camp of tightly coupled multiprocessors where shared global memory address space. And traditional multiprocessing, like symmetric multiprocessing, multicores, are all of that type. But for a long time, these two camps were fighting with each other. And I guess the question for you, so essentially one people say, no, everything needs to be explicit. All the communication needs to be explicit. This is way more efficient than global memory. And other people were arguing for shared global memory. So it's essentially shared memory. So what do you guys think happens? So which of the camp eventually won? Any opinions?
Shared global memory, on the shared global memory, I would guess. Like,
okay, so that's Mustafa's opinion. Anyone?
Assuming we're talking about RAM when we say memory address space, like.
So I had Mustafa saying it's the second type. I guess Bafru saying neither. So any other opinions? There are not that many choices.
I think it's message passing.
What?
I think it's message passing.
Okay, can anyone who pick any particular opinion try to justify their like why do you think one won or neither, or like what's happening?
I mean, for me, it was really just the shared global memory address space. Like in my head, all of them like share the same sort of RAM like address space. That's what I'm basing it off pretty much entirely. So, and the symmetric multiprocessing also sounds like what we have right now. So
got it. So another opinion, so Sankir says it depends on the applications. It's very true. So it's, yeah, someone missed the question, I think, Jack. So the question was, which of the two types, loosely coupled or tightly coupled multiprocessors, are used these days, who won that battle back from 80s? And to be honest, you can give two answers. So one answer is neither one, because there are both systems exist. If you actually go and look at how people parallelize things, you can see things like OpenMP, which essentially represents one form of parallelism. There are things like MPI that still exist and do like for high performance computing. So this is the most generic answer. If you look at their market share, then shared global memory address space is way more common and frequent, and we're all using multi-cores recently. Back in 90s and early 2000s, it was not clear. There was not a clear winner in that sense, or even dominant, choice. But as the multi-cores becomes everywhere, and it was clear that most people are going to use those systems, are not going to write a program with anything explicit. Like explicit parallelism is difficult, essentially. So gradually and gradually, like a tightly coupled multiprocessor becomes more dominant, right? Okay. Yeah, so programming models similar to uniprocessors that help a lot, and operation on the shared data requires synchronization. So it's not like any of that is for free, but it turns out that people prefer to deal with sequential code and then just protect shared data with semaphores and locks, rather than writing send receive messages, although there are cases where the other is much more preferred. So what are the main issues in tightly coupled multiprocessors? So first of all, obviously, shared memory synchronization, locks, atomic operations can slow down execution, can be very inefficient. And there are a lot of other things. We will have to talk to most of them in this course. Cache consistency, or more commonly it's called cache coherence. The problem is when you had sharing and you had individual compute units, they held all the individual memories and individual caches. When this happens, it might be that they have a different view on what is stored in the cache at the same time, because they had their own local caches. And that creates a problem, right? You need to deal with the consistency problem. We're going to have a full lecture at some point to talk about this problem. Ordering of memory operations. That's another problem. Like, what should the programmer expect from what is finished in which order, right? Like if everything's sequential, things are easy, but things are parallel, programmer wants to have some expectations on the order of different instructions to finish. Okay, another problem is resource sharing, contention, partitioning. So any of that might cause some troubles and you had to deal with this. Obviously, there is communication overhead, interconnect, and all of that. You need to deal with that, and load and balance between different, cores. That's another thing you need to deal with to make these things more efficient. Okay, so all those things we're going to talk in this class, right? We'll start with some metrics. Before we can say what is better or not, we need to have some metrics on the efficiency of multiprocessors. And the first thing, surprise, surprise, is a parallel speedup, right? So if I want to use 4 processors instead of 1, I want to see a certain speed up of that, not just burning power and money. So how is that computed? So the parallel speedup equation is very easy. Time to execute program on 1 processor divided by the time to execute the program with n processors. This is the fair metric. But you will see that even though this definition is simple, there are a lot of caveats here that you need to deal with. So I hope you all guys had like a pen or paper or something, or at least a computer to in front of you to do a little bit of warm-up exercises. So I'll give you the first exercise here, and essentially this is we're going to try and parallelize, this, computation. So the first question to you, how quickly you can execute this on a single processor, single threaded machine, assuming that each operation, such as you don't have power, so essentially you had addition and multiplications take 1 cycle. So try to find how fast it's going to run. Like try to write, the execution for that and try to compute how many cycles it's going to take.
So in 1 cycle, we can do a multiplication and addition pair, or like
each of them take 1 cycle. Like just for simplicity, assume that addition takes 1 cycle, multiplication takes 1 cycle, which is actually very common for integer computation these days.
Okay. I'm voting 8 cycles.
Can you do multiply add in a single instruction?
No.
Okay.
My vote is for 8.
Okay, got it. You can just put your vote into the, messages in the chat, and I'll wait for others to try out as well. So just give everyone a little bit of time to warm you up. Those are essentially the conditions. Okay, let's see what you guys think. I had 8, 9, 10, 19 even. Okay. Yeah, I think Mustafa is just going ahead of everyone, but yeah. So actually the naive direct implementation would be 11 cycles if you don't optimize anything, right? So if you just do multiplications, right, directly as it's written here, right? So if you don't optimize, if you use the math the way it is, you'll get 11 cycles. So the question is, after that, how fast you can do this with 3 processors? So try to do the same thing with 3 processors.
Oh, okay.
So assume you had 3 parallel computational units, and you can break it into pieces, how fast you can finish this.
So we count the maximum number of cycles on one processor, right?
Yeah. The processors are absolutely identical. You can, at each cycle, you can do one operations on each of them.
On each, okay.
Yeah. And they assume they can communicate, right? So they can transfer the information, like as soon as the information is ready, in the next cycle, it can be available on the other one if needed, or the input if needed. You know, guys, I'm just teasing you and like making sure you wake up a little bit in the class. Okay, so Mustafa, again, super fast, it's 5, right? And yes, that's a correct answer. So, so someone gets 7. When I tried it many years ago, I got 5 as well. So this is the best I was able to get. Okay. So you just see there's a critical latency here. That it's hard to get it faster than 5 because of this guy, right? And then there are additions. Okay, so this is what you can do in 3. This is going to do in 5. So what is the problem that frequently people that try to report parallel speedup face, and I'm pretty sure you're going to see in your career many times, is the lack of fair comparison. So what people might report to you is by saying that you've seen how I showed T1 was 11 cycles and T3 was essentially 5 cycles. Based on the definitions of speedup with 3 processes, if we divide, we'll get 11 by 5, we're going to 2.2, right? And it seems to be the fair comparisons, right? The question is everything right? Is there anything fishy here on how we did it?
I mean, we assumed like data was instantly being passed over, right?
Yes. But the problem is not with that. I think Mustafa already kind of mentioned that because my 11 is not the best possible. Anyone else wants to speak about that?
When you have more work piled onto a smaller set of processors, there's more opportunity for caching.
No.
Oh, no. I see. You have an 11 there. Like you're not doing it optimally with a single thread.
Yeah, so that's the right answer. So let me respond to Jimmy and then respond to Mustafa. So Jimmy, we assume no cache in anything, but talking about fundamental cache is an optimization. Early machines doesn't have cache, right? So yes, there is some tricks that can happen on cache. We're actually going to talk about it. So you're going to see when people do unfair comparisons, they sometimes get superlinear speedup, and sometimes the reasons why it's not a fake result is actually memory subsystems and caches. But here we're showing something different, which Mustafa already touched upon, which is essentially, I didn't use the most optimal algorithm for a single processor, right? Because of that, it's not a fair comparison. So if you actually use, a Horner's method, right? Then applying that, you will get 8 cycles, not 11. I understand not everyone knows Horner's method or don't remember it from, say, I learned it in high school, for example. But essentially, you take the existing equation and just rewrite it in this form, right? So you never explicitly compute powers. You do this. And the main problem was the original equation. When we compute for T1, I show you the math with 11 cycles for a simple implementation. But when I get 3 processor, there were some optimizations because I had to do it by design. So it happened that I got unfair comparisons between 3 processors and 1 processor because I didn't use the same level of optimizations. And that can easily create problems, right? And you guys are going to see a lot of papers where that pops up. It's one of this hidden things. You always need to look carefully when someone speed up something and parallelize something and they get superlinear speedups. That usually it's either memory subsystem, something related to communication, or they're not doing fair comparison. Like usually it's the latter. Okay, you're going to see this a lot. Okay. So essentially, the real speedup is 1.6, not 2.2, because we didn't use the fair baseline. So the key takeaway from this little exercise that we have is that we want to calculate parallel speedup fairly. You need to use the best known algorithm for each system with n processors. only there that's a fair comparison. Okay, I hope the lessons learned. Any questions about it? Okay. So if you don't get, you can get superlinear speedup. And then the question that I guess partially answered already, or some of you already mentioned, can speedup be greater than P with P processing elements? So when we get, essentially, if we try to get speedup curve, and the number of processing goes, it seems like the best you can get normally is linear, right? Like you can't go that. Most typically it's sublinear. When you get superlinear, as I said, cache and memory effect, working set size fitting, not fitting, that's what happens frequently, and unfair comparisons. So this is the two main common cases. We're going to see the graph with the superlinear speedups. The most of those you're going to see when you're going to read a rant by yet another company saying how their hardware is really good, and they're going to show you a lot of fancy graphs, like saying, oh, we're like 100x better than CPUs and GPUs. And usually the way to get those graphs is these unfair comparisons, right? The marketing people really like it, right? You just take like a single threaded non-optimized baseline on the CPU, and then build their own, dedicated chip and write a super fancy, algorithm on their hardware, and then say, oh, we like speed up things over 100x, right? It happens like every day, every time I see LinkedIn posts with something like that from yet another startup, and if you carefully examine the results, you see this inconsistency. Okay, so now you should be occupied with, explanation for those type of things. Okay, so caveat of parallelism. So essentially, there is a linear speedup that's ideal. Reality is some, curve that's below linear speedup. And why reality is worse than the ideal case? Well, it's because there is diminishing returns from parallelism. There are always, if you take the time that takes to run something on P processors, there is a part of your computation, let's call it alpha, right? That can be parallelized like perfectly, right? That nicely scales. And for that part, with P processors, the time takes to run that part would be T1 divided by P, because everything would be parallelized. But there is also a part that's completely non-parallelizable, sequential code. It's always like that. And because of that, there is this 1 minus alpha multiplied by T1. That's the part that's not parallelizable, and that's because of that, you're not going to look at a linear curve, you're going to have this more like a decaying curve. So if we take that equation that I just wrote, which is very simple and intuitive, and you just, convert it into division, essentially T1 divided by TP, that's exactly the speed up. Based on this equation, what we're going to get is 1 over alpha divided by P plus 1 minus alpha. So it seems to be a simple transformation, but it allows us to make a very simple conclusion. If I increase the number of hardware available for me to infinity, no matter, even with that thing, I cannot go faster than 1 divided by 1 minus alpha. So this alpha becomes a slowdown or bottleneck for parallel speedup. Mustafa, go ahead.
I guess this is also assuming that you can perfectly parallelize your task to use P processors, right?
So this is like from first principles showing the best you can do. So it's clearly you can lose a lot of things. You can be worse than that, but you cannot be better than that. So let's give you an upper bound. So you had a serial bottleneck somewhere in your code. No matter how much hardware I'm going to give you, you cannot go beyond that. The more serial code you get, which is described by like 1 minus alpha, the more, the worse your slowdown is. Okay. So this is how the Amdahl's law essentially was introduced. And essentially, if you convert it using these variables, f is a parallelizable fraction of your program, right? So, and p is the number of processes that the maximum speed up it can get is 1 divided by f over p plus 1 minus f. The f is the same as alpha in the previous formula. So essentially, this is where the famous Amdahl's line come in. So essentially, the maximum speed up is limited by a serial portion. The serial bottlenecks is like a plaque for the sequential execution. This is something we cannot beat. So no matter how much parallelism I introduce, this thing is going to limit me, right? And this is why generations of computer architects spend their time fighting with this part. Branch prediction, all the speculative execution, everything was dedicated to find the serial execution path because parallelism was really not solving it. So some side effects of the Amdahl's law. So depending on how big is the alpha, how big is the parallel part of the code, the better is the curve, but eventually they all look like this, right? The shape of the curve is like that. So essentially the benefit is always diminishing, and it's relatively fastly diminishing, right? And again, the benefit in terms of speed up is small until alpha equals to 1, which really tells you the serial part is indeed critical. So the people who spend 40, 50 years working on the serial code, they're not dumb people. They didn't want to work on parallel because the main bottleneck was on the sequential execution. Okay. So why the sequential? So we just got from the first principles why the sequential bottleneck exists. The question is, of course, then is why the sequential bottlenecks happen. So why the programmers cannot write the code that would be nice and parallel. Well, the problem is that those bottlenecks are unavoidable in many, many cases based on the algorithm you write. So you write a very simple loop like that, where based on the algorithm, the element AI is just an average of the current element and the previous element, very straightforward loop, very common in high performance computing and sort and all this different type of codes where you had some indexing like that. And this code is not like fully parallelizable. It has a dependency that you cannot just easily break. So you cannot take this loop, right, and run each iteration of the loop in a separate thread. They have dependencies, right? So that makes those things complicated. So non-parallelizable operations on data, a problem. Single thread prepares data and spawns parallel tasks. That's another example. So for example, if you had a piece of code that reads the data from somewhere, and then you want to process on this data, that preparation of the data or reading the data is a sequential bottleneck as well. Okay, we got a question. Okay. Yep. Okay. Okay, let's move on. So another example of a sequential bottleneck, more complicated. Again, you don't need to understand this example. I'm just showing the examples of real codes, right? And this is some example with locks and unlocks for a real problem that supports multi-threading. And if you're going to look at those examples, you're going to see that there are part of the code that can be parallelized, right? But there are like critical sections that synchronize everything. So you see there are all those different problems. There are serial pieces of code, there are idleness in the code. All these are the reasons where you can lose, the efficiency. And there is serial parts here, A and E, right? There is B, which is a parallel portion, right? That's this. And within there's like critical sections and outside critical sections. So the problem is there's this parallel things that you can lose performance there for many reasons, and there's also sequential parts as well, such as initialization, spawning threads, printing, all of that can eat up performance. Yeah, in fact, it all hits everyone, even in like very hot fields. Like for example, if you're working on machine learning right now, the last like 4 or 5 years, everyone was accelerating matrix multiplication, right, to death. And now if you look at the existing ML models, they're actually not bottlenecked by matrix multiplication usually. They always get into some other trouble, either with the memory bandwidth or something that is just not computationally bounded, but maybe requires some scratchpad memory. So you always hit some other bottlenecks usually in those models because matrix multiplication was the main bottleneck, was optimized to death, and now there is something else that's usually a bottleneck. But there is a huge inertia in the industry, so everyone still focuses on optimizing matrix multiplication. It's going to take a few more years until people will stop doing this. Yeah, so parallel portion, if done properly, is usually not, even if it's done very efficiently, not perfectly parallel. So there's synchronization overhead, updates to share data, And there are like resource sharing and contention among many processes. So the bottlenecks in parallel portion, there are several major ones. It's synchronization. You've just seen it. They cannot be easily synchronized. Locks, mutexes, barrier synchronization, different form of communications. Tasks may need values from each other. Another problem is load imbalance. So you had two parallel, entities to run context, and one happened to have more work than another. So you get work imbalance. So they're going to finish with different amount of time, and one is going to wait until the other finishes. It can be due to imperfect parallelization or some microarchitectural effects. So one of them can be unlikely to get more cache misses than another one, right? So then it's going to run slower. So this reduces speed up in parallel portion as well. And resource contention, obviously, parallel tasks can share hardware resources, and they might delay each other. They might contend for memory or any other shared resource. Yeah, and replications of everything is just expensive. I guess if you ever built your own, machine or even small server right now, you would know that memory is a big part of the cost of the machine. If you look at the modern servers, it can be as high as 40% of the total cost. So it's not CPU. Even the most expensive Intel Platinum CPU is still cheaper than the memory. And so is different accelerators as well. So memory is usually the most expensive part. And later in this course, we're going to talk about why this happened and how this happened, that it's the most expensive part. And it's usually the one that also causes the most bottleneck. Okay, so what are the difficulty in parallel programming? Well, embarrassingly, parallel applications are easy to deal with. So those are, surprise, surprise, multimedia, physics simulations, graphics. This is why the first accelerators appeared for those applications. So multimedia applications has their, hardware acceleration with a parallel hardware a long time. Like graphics applications, everyone who play computer games know that if you want to be competitive, you need to have a powerful graphics card that's going to do most of the graphic computation for you. And that's used since 90s very actively. Large web servers databases, well, somewhat, but not as much. But big difficulty is in harder to parallelize algorithms, the ones that are not easily, sliceable. Getting parallel programs to work correctly can be a nightmare. It's a very difficult task. Many years ago, when I was an undergrad myself, one of the projects I worked with Intel was on getting a tool that would detect all types of deadlocks in the parallel codes. So someone writes a parallel algorithm, think they work, it usually works, but sometimes on some sequence of event, it causes a deadlock or stops. And then you run it again to reproduce, it's not reproducible. So I was working on a tool that can record just a little bit of the key events on things, so I can actually reproduce those, deadlocks. So you can run it, like you can see what exactly sequence of events lead to the deadlocks. Because sometimes when I have 100 processes, it happens once and never repeat again in years, right? And that's, if you ever debug parallel code, you know what I'm talking about, that can be a nightmare to debug. So optimizing performance in the presence of bottlenecks, even if it works correctly, good luck getting top performance out of it. The performance can be lost in all different fronts. And much of parallel computers architecture is really about designing machines that overcome the sequential and parallel bottlenecks to achieve higher performance and efficiency. So a lot of work, what you deal with parallel computer architecture, is about dealing with either sequential or parallel bottlenecks. So as a parallel computer architect, you occupy yourself with different tools that would allow to analyze the code. You quickly want to identify where the bottlenecks are, where you spend most of the time, and then you try to approach it with different techniques. So making programmers' job easier in writing correct and high-performance parallel programs. So we not only try to make things easy for us to avoid things, we want to make it easier for the programmer to get the performance. So we can write things, we can say, oh, the programmer has to specify X, Y, Z, and then we can run optimal code, and the programmer would just get lost with our requirements. So we need a good compromise between what they ask the programmers to do and what is really needed for us to run parallel code. The rule of thumb is the least the work for programmers, the better it is for your feature being useful. Yeah. Okay, so let's talk a little bit about parallel and serial bottlenecks. So how do we evaluate some of the serial and parallel bottlenecks in multi-core processor We will return to this in the future lectures. Here, slides will be shared as usual after the lecture. So here are some readings on how you can identify the critical sections and bottlenecks from some prior papers. Okay, I guess it's around 2 right now. So I suggest we have a short break right now, and then we return back to multi-cores. So see you at 2:10. Okay, I hope everyone is back, so let's continue. Okay, let's now talk about multicores. Okay, so the first we'll start with a very famous Moore's law. So for a long time, our community was pushing the needle by just putting more components onto the circuits within the same area and similar power budget. This was a driving force from mid-70s all the way until, I would say 3-4 years from now. So for a long time, that was more or less sustainable. So we were able to add more or less double the number of transistors every 18 months. This is the two graphs showing how different architectures were introduced at different periods of time. And you see where we are, and that we more or less follow this exponential curve. Why is it exponential? Because if you look at this curve, this is the year, and this is the number of transistors, and you can see they are on the exponential scale right now. That was something that allow us to go from a very primitive computers all the way to a powerful mainframes of today. The idea is that as soon as that trend is over, and there are different claims, some people, and Intel AMD still claiming Moore's law is still alive, but you can clearly see how Intel itself, for example, struggles with a 7nm process, right? So it's clearly they're not delivering what was promising. They're already like at least 2 years behind the schedule with the 7nm process. So clearly they're not scaling as well as it used to be. So it's obvious because, any exponential law should come to an end, and this is not an exception. There was a lot of pressure on their multicores didn't appear as planned. So people researched them, but one of the problem was that their managers, especially at Intel and AMD, didn't want to listen for their, from their architects. And the architect was saying we're limited, and the main limitation was frequency. And it turns out that eventually they manufacture a chip at Intel. Then when they start to study it, melted. So that's not a joke. That really happened. All the manuals were rewritten for Intel. So the plan from producing 6, 7, 8 gigahertz chips were replaced with something called multicores. So why multicores, and what's the benefit of them? So as technology scaling, Moore's law enables more transistors to be placed in the same die area. There are other walls that you may face. So even if you can put more transistors on the die, you may argue whether that scaling is still there or not, but Dennard scaling is definitely done. So the problem with that, it means I can put more chip, and I'm willing to charge you more on the chip, more transistors, and I'm willing to charge you for that. But there is no way I can speed up your performance easily. I cannot make your chip efficient because I cannot power all these transistors at the same time. So what I do, I just sell you more CPUs, more cores. So because there is no really a lot you can do with it. Well, people would argue that there's something you can do, and that, I guess, was the paper that you review for today that argue about what the future can be. And you can see what this paper tried to predict was really happened 10 years later. But the key, I think I want to say here is that in some case, multi-core was the first and obvious alternative, but it's not as easy as you may think. There were a lot of other alternatives that people consider, obviously, bigger, more powerful cores that not necessarily designed the same way. Another alternative is having larger caches in the memory hierarchy. So because compute is not the only bottleneck, memory systems is also a bottleneck. Simultaneous multi-threading, so known as hyper-threading. So instead of running a single thread on each core, you can run multiple threads on each core, right? And that's known as hyper-threading, or SMT, if you talk with IBM people. And that's an alternative. It would require some transistors, and you invest in that, and you can run 4 threads or 8 threads or even 16 threads on a single core, hypothetically. Another thing, you can try to integrate more components on chip. So if you have more silicon, why not having memory controllers on the die? Right now, this off chip. if you put them, that can be faster, or network interface. Like put everything on chip if transistors are there. Why not? That would speed up things. So all those are alternative. And obviously, architects look at all possible alternatives. And we're going to look at that right now as well, trying to judge why they selected multi-core versus other alternatives. Okay, so why multi-core was selected? So first alternative, bigger and more powerful single core. So if you want to make bigger and bigger core, they're going to face not only frequency issues, they're going to face the issue of scalability of some of the key architectural primitives or architectural artifacts that exist on those chips. So the large superscalar machines have an issue with and how many instructions you can run in parallel. They also had a limit on the instruction window, how many instructions I can deal with in parallel. So questions to you guys, those especially again that took computer architecture classes, why is it a problem of scaling the instruction window? So what's the fundamental problem between it? So why it's harder for me to go from 10 instructions into 20, into 40, into 200. So what's the real fundamental problem with the instruction window on the modern CPUs? Why it doesn't scale well?
I'm guessing the more instructions you have, the more logic you need to decode them. I'm sorry if you were raising your hand and I just spoke over.
No, it's fine. It's related, but that's not the main problem. Like decoding is not usually the bottleneck. Pavel? Sorry, Pavel and Jimmy, I guess. I don't know who was first.
I think Jimmy was first.
Okay, Jimmy, go ahead.
Jimmy, you're muted. You're muted.
You're muted.
I think it increases the cost of misprediction when speculating.
It is, but it's still not it is partially correct, but that's not the main problem.
Okay.
Pavel?
Maybe I'll try. The fuses bypassing, you'll need the n-squared bypassing logic, and the read-write ports on the register file. That's the ones I can think of.
Read-write ports, still less of an issue, although it is an issue. Okay, I'll give you a hint and try to think about it. Most modern processors are out of order. So what makes it complicated if I had to deal with large instruction window if I do out of order?
I guess there's a lot more possible ways of ordering different instructions, and that can get really annoying.
Dependencies, right? So unfortunately, the dependencies doesn't scale linearly, they scale quadratically with the size of the instruction window. And that's the main biggest bottleneck. Things you mentioned, guys, also problems. But before that, the first thing you face is that, right? It's like, okay, someone, yeah, so Behrus said there's more data dependencies. That's correct. So data dependency is the problem. So that's just one example on where those things doesn't scale, right? Even if we forget about frequency and all that, there's some of these data structures that need to support out of order window, right? They doesn't scale. There are more execution units. You can use things called trace caches, that's alternative, and large branch predictors. So you guys know that the deeper the pipelines are, there, you try techniques like pipelining to hide the latency. The deeper the pipelining, the more penalty for branch mispredictions. So your branch prediction becomes bigger and bigger and bigger until they try to get 99.9% instructions predicted well, and the penalty is still high. So those are the challenges. Then what are the benefits of the alternative here? So it proves single thread performance transparently to the programmer. This is a really big benefit, to be honest. So because essentially you can keep speeding up this sequential bottleneck that otherwise doesn't speed up, right? And the programmer and compiler doesn't really need to do anything special about it. It just happens in the hardware. So it's a big benefit, okay? Okay, and what are the downsides? Well, there's quite a few downsides as well. So very difficult to design. So scalable algorithm for improving single thread performance are elusive. People who are not able to figure them out. Power hungry. Many out of order execution structures consume significant power area when scaled. There's a question why here, and I guess I already answered you for some of that. Diminishing returns on performance. So the bigger it becomes, it doesn't mean that performance scales linearly with the increase in size. And it does not significantly help memory bound application performance. So scalable algorithm also difficult. Okay, so what are the alternatives? So if you compare, again, large superscalar versus plus out of order versus multi-core, that was one of the first papers that looked at that hypothetical scenario, the case for a single chip multiprocessor back in 1996. Remember that it was 10 years before Intel started to look in multi-cores, right? So this is why the value of academia is to look at the problem before industry faces them. So Kunli looked at that problem back then, and he shows here a floor plan of the two chips. One chip is this big fat out of order core, and you see things like instruction fetch, instruction decode and rename. And this is the thing I talk about, reorder buffer with instruction queues and out of order logic, the biggest part, right? This is what you need to have if you want to have one big fat core. On the same area, you could build something with 4 processors, right? Single chip multiprocessor, and that's essentially uses the same area. And then you can evaluate and see when one works better versus the other one. And they had similar memory hierarchy, so they had the same L2 cache. So this is where the trade-offs, if you had more of smaller chips versus one but fat chip. So what are the multi-core advantages versus large superscale or out of order? Simpler cores, more power efficient, lower complexity. Easier to design and replicate, high frequency, shorter wires, smaller structures, all these benefits. Higher system throughput on multi-program workloads, reduced context switches, and high system performance in parallel applications. That's the advantages of multi-core, which academia identified quite early. It's just not everything was ready then. And the disadvantages are it requires a parallel task and threads, and all of this parallel programming thing needs to be there. I remember when I was finishing my undergrad, people just start to realize that multi-cores are unavoidable, and the whole curriculum has to change. So students out of a sudden needs to learn parallel programming, which was never a part of the main curriculum for undergrads anymore before. And now it is needed because otherwise you cannot program those machines. Resource sharing can reduce single thread performance, obviously. Shared hardware resources needs to be managed somehow, so you need to access extra logic to do it. Number of pins limits the data supply, so you cannot feed all these cores potentially with memory, right? Because the number of pins coming into the chip is, spatially limited.
Sorry, can I add a quick question? On the previous slide is you said parallel programming, right? That needs students needed to learn how to program parallel machines. Are there any automatic tools that given just sequential code written by a programmer that break it down into parallel?
Very good questions. Before I answer Pavel's question, anyone wants to try to answer? So given a sequential code, like people who took theory classes, can you automatically parallelize it in general case?
I mean, you could, it just wouldn't speed up.
I guess, so there are, depending on how you formulate this problem, that any general formulation, it's either, NP complete or undecidable. So it's like the general case essentially don't have solution. Having a sequential code, finding a way to parallelize it that improves performance is actually a very non-trivial task. So it's all limited to just some use cases. So like 10, 15 years were spent by people claiming they can write, they can take like regular spec benchmarks and parallelize them automatically. And I had a lab mate when I was a master's student at UofT who was working on this thing during his PhD for 5-6 years with no success, despite the theory clearly say it's in general case, it's not a solution, right? So the short answer is people realize it's impossible. So for practical, through a lot of empirical evidence. So you need some help from the programmer, so they had to rewrite your code. If it would be possible, we wouldn't have CUDA, we wouldn't have OpenMP. So no one would have to write their code differently and restrict your algorithms, it would be possible. So it is possible in some contexts if you use a different programming language or extensions to existing programming languages, but it restricts the algorithm you can do with it. So it's possible for certain classes of applications, but not in general case. So the general, like someone was trying to figure out this for a general, it's like a general C code, and that's not, it's a big no-go, yeah. Okay, those are the typical comparison points. So you get a one, 6-way super, simple scalar machine versus 4 two-way multiprocessors. Those are our comparison points. And like on different applications, one or the other has advantages. So it's not like one is always better than another one, right? Back then, there was still latency was dominant. There were not a lot of parallel applications that like Intel didn't buy it, right? Like researchers, they know about the potential of, simple multiprocessors, but the people who are not still into it. But, 10 years later, they would have to go in this path. And I guess Intel was lucky that academia research how those chips should look like by the time they have a need for them. Another example, canonical example, does anyone knows what was also invented in mid-90s that Intel only deployed in 10, 15 years later, also related to parallelism?
Is it hyperthreading?
That's correct, good answer. So hyperthreading was invented in mid-90s, and I guess the first paper was from a Japanese guy, either Iska 1994 or 1995, but he wrote a paper so poorly, so no one really understands. So 2 years later, the same idea was reinvented. With the new terminology, and that's where hyperthreading was introduced. And it took another more than 10 to 12 years until Intel finally has hyperthreading of two things into it. Yeah. Okay. Another alternative, bigger caches, right? So yeah, Mustafa.
So why do you think it takes so long for like a hyperthreading clearly seems like a good idea, but like why do you think it takes so long for like stuff to be adopted?
Very good question. I think there are several aspects to it. And I guess I had my own experience with Intel. There are fundamental reasons of the design that limits things. So essentially, if I come to Intel right now and propose an amazing idea, it's going to take until 4 years that something make to a real chip. This is their, cycle of development, right? That's one problem. So they're not as agile as, say, NVIDIA, for example, in designing their chip. NVIDIA generates, well, they claim every 1 year, really the hardware change every 2 years, but still much faster, right? TPUs, at Google, I think they had iteration every 15 to 18 months, but this is the typical cycle for the hardware. Another problem is, so when you propose the idea, the radical ideas always has a lot of open ends, right? So that people have to figure it out. So usually the first feedback from industry on anything radical, oh my God, we're never gonna do this, it's too complicated, right? That's impractical. Industry is only driven by, like they need to face the wall and sometimes smash their head and by that wall, and then they feel that the problem is there, right? So not a lot of managers in industry going to be very proactively looking for what's needed and when they're going to face it because they're driven by the deadline. So in one end, their cycle is very long, like 4 years, and the other end, they had a lot of internal deadlines. As a corporation, every 6 months there's some deadline. So like when you had a very short fuse deadline, you always focus on small hacks rather than big proper solutions. So this is what limits it. On top of that, that's generic for big corporations. And then companies like Intel has their own issue of an extreme conservatism on applying new techniques. So you can come with them and they give you feedback. Like I spent 3-4 years in talks to Intel in my PhD thesis on implemented in real hardware. You first solve problems for them and then you realize, you know what? They just don't want to do it. So it's really not fundamental anymore. And then you talk to someone like, I don't know, smaller companies like Qualcomm, and they go and implement your stuff. So it's important to talk to industry. They're going to push back you on any possible place where your idea might break. And you need to take this criticism and, improve your idea, fix the problems that left. But eventually someone has to go and write, the Verilog code and tape out the chips. So there is some engineering that need to go there. You need to justify them that the risks are reasonable, but if you don't take the risk, you're going to be like Intel right now. I think we got a question.
Sorry.
So Behrus is asking how Tesla does it so fast. I don't know too much of the corporate ethics in Tesla. I just had one collaborator in MLPerf who works at Tesla. They are clearly much, they had way more initiative given and independence given to the individual developers, the pushing their decision than Intel. Like, I think Intel has the same problem inherited from IBM. It's like corporate culture and the ability to push new ideas is extremely slow to my taste, even compared to like other big companies like Amazon or Google. It's a separate discussion how each companies are different. I can see for a lot of companies has their pros and cons, but there are general trends. Like the bigger the company, the slower the things. And Tesla is only relatively recently becomes large. It's still the core engineering corpus is still really tiny, if you ask me, right?
I just have a comment, I guess.
Yeah. So some state in a link saying it's 18 months. And so just give you some sense of, for example, the first iteration of the TPU chip, which was inference engine, the simplest that's possible, that was 15 months. So that's what I've heard. So this is pretty much, they really push the needle. They get the best architects possible hired by Google, trying to push for that. They hired Dave Patterson from Berkeley. They hired Norm GP from HP. So the people that know how to build chips, right? And even that's still time-consuming process, right? Especially if you do something radically new. Yeah, but I think the reason, like coming back to the original Mustafa's questions, why it, sorry, I forgot who asked the question. I think Mustafa was like, why it's taking that long, right? So I think the engineering is a part of it, but I would say it's 25–30% of the time that's engineering. And then there are other things like you need, like the people like to keep the status quo. Like people had a replacement policy in Intel and they're happy to stay with it for like generations, right? They just keep tweaking it a little bit with every single CPU. And there's a lot of tendency not to go in the wild and see what's needed. Like Intel likes to keep building, chips for, for laptops and big machines. And then the mobile came, they completely missed it. Like the Atom chip, which everyone knows about it, that was like complete mishandling. I know the people who designed the chip, they're actually good architects, but they get completely wrong directions on what the power consumption and everything would be. Because like inside Intel, they didn't have a good clearance on what they should build it. And another canonical example I think everyone heard about, right? About the biggest mistake their previous CEO did, or probably not the previous CEO of Intel. Now they're changing CEOs quite frequently because of different issues. But essentially when he was asked, I forgot the guy's name, what was your biggest mistake? He said that essentially, Apple came to him and offered to build the chip for something that was later called iPhone. And you know what Intel's response for that was? There's no market for that thing. That was the very famous response from, from Intel. Well, if that's the deep analysis you do on the market of things, and that's the response you give for opportunities, right? Like they decided not to fabricate it. Apple said, okay, we're going to do it ourselves. Right, yeah. So, but yeah, they could be part of iPhones, for example, and they could have a real mobile market. Can you imagine that the mistake like that, like at the corporate level? Yeah. Anyway, so it's like Intel is pretty much still the company. When I was an undergrad, beginning of 2000s, that was pretty much the company everyone looked for because IBM was on the decline and everyone was looking for Intel, right? And really Intel didn't learn, in my opinion, anything from IBM's failures. They just completely repeat the history of IBM and become the company that's becomes outdated. They keep losing people by this date. Like most people already they keep losing still people. I don't know how long it's gonna continue.
Quick question.
Yeah.
What's your opinion on AMD versus Intel?
So AMD for a long time was just a shadow of Intel in the CPU world, and they were trying to compete with NVIDIA, although not particularly successful. I think they bought ATI at some point, and they did into graphics market. So but they never were the major competitor for both. I think I don't remember how many years ago, but they got a very new and active CEO, right? The company, she's winning a lot of different awards recently. but it's not the words that really matters here. It's the work that she did. So she actually, with that kind of the lack of real progress from Intel, AMD figure out how to move forward. So after so many years where AMD was always behind Intel, now finally they produce chips that are actually better, on par at least with Intel. They got into 7 nanometers faster. They're producing chips that are competitive in the price range. And they're even trying to put some pressure on NVIDIA, although NVIDIA is a separate beast. And by the way, everything is recorded, so this is all my personal opinion on all these different companies, right? So there's no real full truth about that. There's just opinions. But I think AMD right now is, the raise of their stock is not just a boom. They do actually deserve a lot of credit recently, especially flops from Intel, and to help them a lot. I guess with NVIDIA, it's not like NVIDIA did poorly either. The main opportunity here is that NVIDIA was really dominating the market and put the price range very high. That's where it creates opportunities for AMD to start to compete a little bit. But still, their market share is incomparable, in my opinion. It's like, I think NVIDIA is close to 80% or something, right? The market share on the gaming market.
Have you seen the prices for 3080, 3070? The 3070 is better. 3070 at $500 is better than 2080 Ti, and 2.5 times cheaper. There's a lot of memes on that, on the internet about that.
Yeah. So the new chip is coming. I missed the opportunity. I forgot about I didn't put a notification, so that was possible to buy Founders Edition of 3080 today, and it was 6 a.m. Pacific and 9 a.m. And like I was dropping my daughter at school around 9. And by the time I returned home, like 9:10, it was already out of stock. So I kind of missed it. So I always want to buy one for our lab to play with it. I guess the next chances are going to be 3090 next week. 3019 is more interesting because they're really pushing the envelope, but they also power constrained, so they are 350 watts. So we need to make sure it's going to work in one of our machines. But yeah, we're going to get one of those to try out. I guess I'm also very proud that we get alpha access from Google to 800s. So the 800s are the new GPUs from NVIDIA, like they're not available for sale only in the cloud. And we get the early access to the Google Cloud. Even Amazon and Azure still don't have that for internal use, but we get access to those. So it's very interesting to play with. Okay, in the interest of time, we need to move on. Any other questions? Yeah, so that's a good reason. So that's something I really want to see in your discussions on those papers, because I give you papers not too old, but somewhere those are not trivial papers. They try to make prediction and you can see what really happens, right? So it's very interesting to see where the market really pushed, where people were saying something is not possible, right? Yeah, so Alex, that's a very good point. Okay, let's move on. So another alternative is bigger caches. So improve single thread performance transparently to the programmer and compiler, simple to design. Well, it's easier to say than do, but caches, after you figure out how to do replacements, are relatively straightforward. The problem with caches, they're diminishing single thread performance returned from cache size. The question to you is why? So why, if I'm, keep increasing the cache size, why performance is not scalable? So what happens? So if I'm going from 2 megabytes cache to 4, from 4 to 8, from 8 to 16, why it's not really scalable?
Does it have to do with cache eviction?
It does. So it's not just cache eviction itself, it's the whole process of the size of your working set size. So the problem with the caches, it's not like they linearly benefit you, right? If you get more wires, right, they just linearly scale your speed. But if you get larger cache, it really depends on what is the size of your working set. Yeah, there are some other downsides. We're going to talk about caches in a lot of details in the future lectures. But the single thing, the rule of thumb that people use, there's a square root rule. So as you increase the cache capacity, the performance is not going to go better than the square root of the scaling factor. And multiple levels of caching complicate memory hierarchy. We're going to talk about this in the future when we talk about memory, caches and memory. So essentially, if you think about, I'm an engineer, I have a budget of transistors that are given me by Moore's law. I can use them differently. So what happens in a very coarse-grained figure, at the beginning, I just keep increasing the number of cores, right? And I also want to increase their caches. And at some point, you know, what's going to happen is my caches to support this multi-cores go to that level that I cannot do this anymore. So instead of having this transistor spend on caches, I start to spend them on more microprocessors. So I'm going to show you some designs of existing chips. You're going to see just visually that easily 40 to 50% of the silicon is spent on the caches. Okay. Okay, another alternative, simultaneous multi-threading that we mentioned was invented in the mid-90s. So it exploits thread level parallelism, just like multicores, and it helps with achieving good single thread performance. There's no need to have entire core for another thread. It's really beautiful. I think it's one of the really cool inventions. Hyperthreading is that I can get parallelism with not replicating stuff, because getting parallelism by replicating the core, it's not, you don't need to be super smart, to come to that. Figuring out I can run 2 threads on pretty much the same hardware with really minimal changes, that's really, a little bit of a genius of idea you need to have. So parallel performance aided by tight sharing of caches, that's the benefits. The downside is it's not very scalable. It's one of those tricks that you do, it's really good, right? But it doesn't scale. So it's not like the Moore's law that allows you to scale transistors. So transistors, an invention, is really incredible because it allows to keep scaling. It's scaled for 50 years almost, right? But simultaneous multi-threading, we started with 2 threads. It took another years to go from hyperthreading to SMT2 to SMT4, right? So it's not an ultimate solution. This is nice, cute trick, but it doesn't scale and becomes very complex with many threads. Parallel performance limited by shared fetch bandwidth. Extensive resource sharing at the pipeline and memory system reduces both single thread and parallel application performance. So those are the kind of key downsides. And practically, I can tell you that one issue with dealing with SMT is when I'm given a particular application. Right now, most cores, you'll have most multi-core and multi-threading. So it's very non-trivial which configuration to go. Say I had a Power 9 chip from IBM that has 8 cores or 16 cores, and each of them has 4 threads. So which configuration I should run? 4 cores, 2 threads, 8 cores, 1 thread. There's all this configuration. Optimality is very hard to figure out. So a lot of people just give up and don't really optimize anything. Just a second. Okay, so another thing is speeding up many system functions such as network interface, Ethernet controllers, memory controllers. That's another option. The main downside to that, no applications benefit really from that if it has the specific features. If you had CPU-intensive code, you don't really benefit from it. It's really use case specific. All that said, one of the sub-teams of Microsoft Azure Catapult project, they actually implemented the networking protocol. Think about TCP/IP purely in hardware. So they took TCP/IP because that was their bottleneck. They don't want to pay milliseconds latencies for the access because TCP/IP essentially was bottlenecked with some CPU level code. And they just rewrote that protocol for themselves in the pure hardware using FPGAs. So FPGAs use like a networking devices there, and they can go to microsecond latency instead of millisecond latencies. So it's not like, if you look at scale, like at the cloud, it might be worth doing it, but if a single app, it might not be beneficial. Another alternative, traditional symmetric multiprocessors, smaller die size, more memory bandwidth, no pin bottleneck, fewer shared resources. Those are the pluses of traditional symmetric multiprocessors. The downsides are long latencies between cores. You need to go off chip so that communications frequently kills you, and worse resource efficiency due to less sharing in general. Okay, other alternatives. Well, there are still a lot of other alternatives I'm not going to talk about that people are looking at. Clustering, data flow, vector processing, integrating DRAM on chip, or integrating computation inside DRAM. This is all alternatives. Reconfigurable logic, something like FPGAs. Can you make it general purpose? A lot of people working on all these alternatives. So there's not like an answer to say why multi-core is the best. Essentially, it's all a lot of trade-offs, and different, like several companies that push the needle figure out that that seems to be the best trade-offs out of the options available to them at the time when they make the decisions. Yeah, next week you're going to review the paper from Karu on exploiting ILP, TLP, and data level parallelism, all these different form of parallelism with the polymorphous TRIPS architecture. TRIPS architecture is data flow architecture. This is not the usual architecture, so that's why you're reviewing it. Today I'm going to cover more classical architectures, but you're going to read about data flow architecture. This is probably different from everything you've seen before, right? This is where it's not the instructions are the boss and driving the execution. It's where the data is driving the execution. So the data activates the compute, not the other way around. Okay.
Could you repeat the last like 15 seconds?
Okay. So what I was saying is there's work by Caro that's going to review for the next week. You're going to learn about different types of parallelism in this new architecture called data flow architecture. And it's radically different from everything you've probably seen before, because you're not going to, this architecture is not driven by instructions, it's driven by data. So the data as a parameter activates the compute, not the other way around. So it's not like you have instruction in place and the parameters arrive to it later. It's like you just really looking for the data to be ready and then compute arrives to it. So it's the other way around. Okay. So this is the brief summary. I guess we're not going to go too much over it. I still want to cover some interesting content today. Okay, so I talked about multi-cores, and it's all still was kind of in vacuum, no figures, no real chips. So now you're going to see a lot of chips, right, one by one, because right now you're occupied with the basic knowledge on how to compare them. So I'm going to show you a lot of them. First of all, this is relatively outdated slides, but I think it shows enough complexity. And to be honest, you know, in the 5 years that came from the last, from the newest chips in this list, nothing radically new came up in this space. So they just, you know, getting a little bit more cores, a little bit more optimized, a little better transistor count, nothing really radically different if you ask me from the architecture perspective. The only real difference here is probably systolic architectures and TPUs, but they're very different from this general purpose chips. What do we have here? We had the older Barcelona chips, AMD Barcelona, 4 cores, have Intel Core i7, used even currently, 8 cores. I think I told everyone you see this huge structures called shared L3 cache. They're as big as the cores themselves, right? They're really humongous. This is IBM cell processor that was popular. I don't think it went anywhere. This IBM Power architecture, Power 7. I think the newest one is Power 9, just recently announced. Oh, someone has a question. Yeah, 9, Power 9. Yeah, so that's the most recent one. There is chips from Sun, 8-core Sun Niagara 2. There's NVIDIA Fermi, this very old NVIDIA chip. The new chip looks very different. There are Intel SCC architecture with a lot of cores. That's where people tried more radical designs that didn't work out that well. There's also Tylera cores. That's a company that was started out of MIT and eventually was consumed by one of the networking companies, something Mellanox. So Cisco, I don't remember, someone bought Tylera. But essentially they got really a lot of small cores, right? Wimpy cores. They all connected with network. Okay, so with multi-cores and chips, what we want is we want n times the performance with n times the cores than when we parallelize an application to an n cores. That's what we want. So what do we really get? That's the goal. In reality, we had Amdahl's law with a serial bottleneck, and the bottlenecks in parallel portion as well. So one problem is serialized code sections. Many parallel problems cannot be parallelized completely. So all those are all the limitation factors that we have to deal with I mentioned them before: sequential portions, critical sections, barriers, limited stages in pipeline programs, uneven load on the cores. That's another problem. Serialized code sections reduce performance, limit scalability, and waste energy. So what we really want is, in a serialized code section, we want one powerful large core, and in parallel code, we want many wimpy small cores. This is what you really want as an architect, right? That's what would be efficient. And these two conflict with each other. And if you had a single powerful core, you cannot really have many cores. If you had a small core, it's much more energy and area efficient than a large core. So there's this trade-off between large versus small cores, right? So large out of orders versus small in-order cores. And large cores are power inefficient. So usually rule of thumb is you get 2x performance for 4x area and power. That's what happens. This is what the trade-off is. Mustafa, go ahead.
So what about like the composed architecture, like the paper was talking about? So like we have one core that can like logically fuse together, like multiple smaller cores can logically fuse together into a larger core.
Yeah.
Like that seems to have the benefit of both, really.
That's correct, and that's where research went. A lot of papers published. One paper is called Morph Cores, got the best paper micro award. What is the final result of that? No impact on industry. Like, try to guess why.
Intel didn't like it.
It's not just Intel. They are fundamentally really difficult to build. So in your simulator in the paper, you can hypothesize on anything you want, but the practicality limitation. So people build this Morph cores where, like, say 4 small cores can just, like a transformer connect and becomes like one big core. Looks super fancy, but good luck building a transistors, or like, not transistors. Try to build a data structure in out-of-order core that would create you a huge out-of-order window out of some structure that has nothing to do with out-of-order. So you had 4 small in-orders, and you want to make one big out-of-order. How are you going to do it? Like, how are you going to build, from the logic gate, something that would be so nice and amorphous? So from a theoretical perspective, that seems to be a great idea. People try this out, right? But how to do it dynamically is very difficult. If you do it statically, that people build those chips, they all failed because you cannot ever figure out the static ratios right. You're always gonna have bad performance on one application and bad on others, and those average applications you're aiming for might not exist.
So you would have to have like out of order logic there just in case, I guess?
People build something like one large core and 4 small cores all together. The problem is then if you get an application that have a really serious, critical section, they would rather have 2x larger core than 1 large and 4 small, right? So people tried it. There are a lot of proposals. None of that really make it to an impactful product. So there is another part of the work of computer architect. That's something that's very hard to quantify is complexity. This is part of the art of computer architecture, how to design something that's practical and actually implementable. In this case, I don't think that Intel was against it. It's like everyone who tried very quickly realized it's a very difficult task to implement. Yeah. So one of the small cores, that was something Sun passed. I hope most of you've heard about Sun Microsystems. Like when I was an undergrad student, it was, really one of the top companies to look for until they got into trouble. And I mean, they do invent a lot of really cool stuff. Then they were consumed by Oracle, and I guess most top people left the company. Yeah. So they introduced some of the first small multi-core chips with a very aggressive multi-threading. So this is a small 32-way multi-threading Spark processor. Remember, 32-way multi-threading here, and we're talking about 15 years ago, right? Something that most people cannot build right now. So they had a 4-way fine-grained multi-threading, 4-stage dual issue in-order pipeline. There's an order part. So now everything I'm going to say in this slide shouldn't be cryptic for you. Now understand what I'm talking about. 4 ways about multi-threading. 4-stage is the depth of the pipeline. It's dual issue, and it's in order. Round-robin thread selection, scheduling, and shared FP units among cores. That was their design, and this is the application they look for and they try to optimize for. So they will keep pushing on this design, and you see things were gradually changing as they realized the reality of the workload they has to deal with. So there were 8 Spark cores here in UltraSpark and Sun Niagara 2, 8 threads per core, 8-stage pipeline. You see pipeline become deeper, they get more caches. Add a lot of fancy stuff there, graphics scripter on cores, which was unusual back for the day. Yep. So this chip was quite interesting and radical from the research perspective. That's amazing that they tried out, because commercially it was not particularly successful, and there were a lot of reasons for that. Mostly, I guess it was manufacturing and everything was not as useful back in the day. So essentially there is this dependency. You can make a really fancy hardware, but if applications are not there yet, all this parallelism is wasted. So back in 2005, 2006, there were not a lot of multi-threaded applications, right? So essentially hardware was ahead of its time somewhat. So it's the same story with like, iPhones, right? A lot of people tried the same idea of something, a small computer in your hands, right? I use like a small HP devices way before before Apple, but they never make it to the right time when you say have the right internet speed. So those small HP devices that I use that were before iPhones, the main problem there, they were not really connected. You can read books on them and play games, but they were not connected with the world with a good connection. So there was like the mobile networks were not ready for breakthrough yet. Okay, some discussion going on in the chat. Let's move on. So meet small but larger. So Sunrock. So this is the follow-up. So they realized that small is cool, but the performance comes from larger ones. They start to build larger cores, and that's, I think, one of the last chips that Sun built because they were acquired. Simultaneous speculative threading and all pipeline architecture implemented in Sunrock's processor that was an ISCA in 2009. So they even spent time before dying out on publishing ISCA, which is quite impressive. The goal was to maximize throughput when threads are available. They boost single thread performance a lot, and I really thought that was a really cool chip. There was several ideas they try out that I guess one of my advisors was very happy with. They tried run-ahead execution that Honor Mutlu invented in 2003. That was cool. The not so cool thing, it turns out that it doesn't really work as well as it showed in simulation. So I don't think it went into any other chips moving forward, but it was tried out in a real chip. Yeah. So what's the question, Mustafa, about ray tracing, so I can answer the question?
No, I was just joking because the chip had like an RTX section on it. So you said it's ahead of its time.
Okay. Well, NVIDIA was not too much ahead of the time. They released it a bit early because nobody's going to build a game, without hardware support. They had to solve that problem and invest into silicon that would be dead at the beginning. I would rather buy 2080 Ti without RTX thing, for example, but just not available, right?
No, I meant on the Sun chip you showed on the page before. There was like an RTX section on it.
I see. Okay, that's a different thing, yeah. Another thing that was unique for Sunrock was a branch predictor with a global sharing. So it was a very more radical branch prediction that exists before Intel. And that's how it looked like, 16 cores, 2 threads per core. So you see what was happening. They started, like they tried experiment with 8 threads per core and 4 and then 2. You see how SMT was, produced because there's a cost for SMT and there were little benefit because applications were not ready. So they couldn't find customers. They would actually run this efficiently. So, and they start to use much larger caches in some cases. Okay. And this is how it compares what they propose, which is black versus out of order design, which is their previous prior design on the application they care about, which you don't need to know right now. They're old, outdated anyway. Okay, then IBM always work on large cores, although IBM also has a very funny story behind them. So Sun cannot figure out how many threads to use. They were going between 16 and 8 and 4 and up to 2 threads in SMT. AMD couldn't figure out where they should do in order or out of order. So it's usually in Intel, it's very systematic. They switch, they start to do out of order and they stick to it. IBM had flip-flopping. They went for, I think in one architecture, they were out of order, then they switched to in order. And then it all failed, and then they switched to out of order again. I don't remember whether it was between 4, 5, and 6, power 5, 4, 5, and 6, or 5, 6, 7, but they had this flip-flop once. So they had this issue internally that what should go was in order versus out of order. So yeah, power 4 was out of order, definitely. I don't remember whether it's power 5 that was in order or power 6. Yeah, I think it was power 5 that was in order and power 6 then was out of order again. Yeah. So 2 cores, 100 entry instruction window is your very deep instruction window, 8 wide instruction fetch, so very wide, very fancy large core, large local global hybrid branch prediction, reasonably large L2 cache, although not super large, and aggressive stream-based prefetching. So IBM was always one of the most advanced companies on the prefetching end. And this is power 5. P5, and I think, yeah. So okay, so that I was wrong. So this is where they switched. So power 5 was still out of order. Power 6 was in order. So power 6 is in order. So they had some justification for that. They were able to make it in order. It's just 2 cores, but they had a very huge frequency. So they thought they're going to deal with serial bottleneck by increasing the frequency, right? So no one has frequency of 4.7 like 13 years ago, right? That was a very high frequency. So in some sense, they also try run ahead execution. And most of the things didn't stick. High frequency didn't pay off. Run ahead didn't pay off. And in order was like a terrible idea. Well, so later on they switched to, I don't show it here, but Power 7 chip has out of order again. And since then, they stick to Power. I don't know what's happened with their architect of Power 6 who make the decision, but yeah, that didn't stick. And in general, I actually work at IBM back then when the Power 5 and Power 6 was used there before Power 7 was introduced. And yeah, I don't think Power 6 even was used actively, even internally. I think it was a failed chip. Okay, there are many more available. There are wimpy nodes like Telera, there are symmetric multicores, there are DVFS, and I cannot cover all of that. I just encourage you to read more about that if you're interested to learn about more and more radical chips. So the only thing I can say today is that 10, 15 years ago, it was quite boring to be a computer architect because industry thought they had their way through. They didn't listen for you and they do whatever they believe and you do your research completely independently from industry. They don't see a lot of value in you. Now things are very different. Things keep shifting. Architecture clearly plays a big role. It's just so obvious. Just look at what happens with Google, Facebook, and Amazon, pure software company that now hire large hardware departments. You see what happens with Apple that starts to tape out their own hardware as well, right? So clearly everyone wants to be, fully integrated down to the hardware and produce their own silicon. So clearly it puts a huge demand on computer architects. So put huge demand on compiler experts. That the highest increase of requests on LinkedIn I get for my compiler expertise. That's where I guess companies really struggle right now in finding the right talent. So which means there's many difficult problems that industry faces because then our scaling is over. Moore's law is pretty much over or nearly over, right? Depending on how you define it. So it creates a lot of opportunities for you guys to benefit. So it's bad for industry, it's good for, for students. All these interesting problems are here that I mentioned already. Yeah, these problems affect all parts of the computing stacks. If we do not change the way we design systems, so we need to think about the full system stacks to make a real impact. And you can revolutionize the way computers are built if you understand both the hardware and the software stack well. you can invent these new paradigms for computation, communication, and storage. And if you want a really encouraging book about how to make, a next scientific revolution, read this book of Structure of Scientific Revolutions. Okay, I think, but before going into these radical things, let's understand the fundamentals. You cannot change the world only if you don't understand it well enough. So especially the past and present dominant paradigms and the advantages and shortcomings, the trade-offs, and this is what this course is about. Okay, sorry it took you a little bit longer today. So thank you a lot, guys, and I really like your questions. So please keep asking questions, and that's very helpful to make it more lively discussions and get a little bit of a real feeling of a real lecture. So any questions?
There was a runaway execution in the IBM Power 6. What does
run ahead? Run ahead.
Run ahead, right? What was that? I've never heard.
Yeah, so run ahead execution is something that Honor invented. Is essentially the way in which when you had a miss, right, in the cache, instead of stalling and waiting for this miss, you speculatively continue the execution. Why is it useful? Because even though you don't have the value of this instruction, you might keep executing and you discover other future to happen misses. And since the you want to overlap these two misses so they won't happen not sequentially but in parallel.
Okay, I see.
Yeah, you can read the papers for more, but it's a speculative technique that uses essentially the parallelism, in the existing parallelism in the hardware, and exploit the memory bandwidth available that's usually underutilized. Okay, guys, any other questions?
I just had a side question, if you don't mind.
Of course, go ahead.
I was wondering what's your thoughts on industry or AMD specifically moving to putting multiple dies to support even more cores?
My honest answer to that, and I'm not familiar with the most recent design, I think it's still the way for them to sell more transistors to you, right? So essentially there are limits on the when you start to deal with multi-cores, right? We just touch the cores, but it didn't touch the other aspects, like memory subsystems. You're gonna see that those structures don't scale well. So you would have to figure it out, and they just try and to keep building a stack of layers so they can sell it to you, right? So it means that some technology arrived that's available, but it also means they're trying to find a creative way to sell more transistors to you. Whether the regular application will benefit from that and how you're going to extract parallelism for that is still quite unclear. Right?
Okay, thank you.
I mean, while we're on it, what are your thoughts on Apple moving to ARM or ARM chips in general? As far as I am aware, I don't know if you can use them with a traditional, they're not super compatible with traditional GPUs at least.
Mm-hmm.
Most of the ARM devices I've seen have their own integrated smaller GPUs.
Well, Intel has integrated GPUs as well. If you look at the market consists of 75 to 80% share of NVIDIA, 10, 12% of AMD share, and then whatever 7-8% of people that are using integrated GPUs from Intel. I don't know how to play games with it, but they somehow.
No, I meant for specifically ARM chips, ARM.
Yeah, ARM chips is interesting. Although right now ARM, it's not acquired yet, but it's hopefully soon to be acquired by NVIDIA. So I know it's going to happen.
Yeah, especially with that and Apple's move towards ARM chips. What do you think the implication is going to be on processors?
I had my opinion because one of my best friends works at Apple, so it's I do have some insight, but I guess I don't want to comment too much. It's just if you just look at whom they're hiring right now, you can get a feeling of what Apple is trying to do.
Apple has sort of not a conflict, but with NVIDIA, right? You won't find an NVIDIA video GPU in an Apple computer, right? So now with NVIDIA buys ARM and Apple wants to use ARM's processors, what's happening?
It's going to be an
NVIDIA is going to be if you want to use ARM, you better move back to our GPU.
That's right, yeah.
Yeah, it's going to be an interesting, story there, especially there's so many companies depend on ARM so many players in the space. There's also this big startup started by Berkeley, people that I know at Berkeley, Sci5. They're looking to push, open RISC-V architecture. So now they might be very relevant because people would need another ARM. Like people want something independent and just want to run technology from it. If ARM becomes NVIDIA, NVIDIA use it as a bargaining chip, then people would start to lose interest in ARM. They want something independent again. Might be a good thing for these guys. Also, regulators might still not approve the deal. So it's like these big deals needs to be approved by like pretty much everyone. British regulators, US, China. We'll see how that works. Like too many people depend on ARM right now. Okay. Any other questions? Okay, a question about late policies. Oh, that's a private question. Yeah, so if the questions on Piazza was missed, or if you ask something, just pop it up, make sure it pops up, and I'll try to look at it. MTA might miss it as well. Yeah. Yeah. Okay, any other questions? Yeah, well, usually this is a grad level class. We don't really, had any specific late policies, but if you're late for some reason with your, reviews, you should notify TA and we'll back to you and say when you can submit it. But we cannot really handle if it's too late. Yeah. Any other questions? Okay. Thank you guys, and sorry that it took a little bit longer.
Oh, it's fine. I like the discussion and the stories.
Okay. Okay, thank you guys. Well, that's the point, right? If you don't want just the boring stuff, right? You want some stories as well. Okay, thank you.
Bye.
Thank you.
Thank
Thank you,
you.
guys. Thank you.
Thank you.